Yeah. Thanks for that. Yeah. So yeah, my name is Matthias. I'm usually just called Matty. It's simpler for everyone. And yeah, I'm gonna. So I'm calling you live from the studio, right? And I'm gonna be talking about some of my recent work, like things I've been doing. Yeah, like since June or March, but it's kind of part of my PhD story. Okay, so let's see here. Let's open this up, and then you should all be able to see it. Okay, so yeah, so I'm Tritlo on Twitter, and so yeah, this is the title of the talk: Weakening Type Systems for Faster Prototyping. Okay, so we kind of all know what type systems are, right? They're good. So they allow you to impart a partial specification of your program up to the compiler. You can tell, So, and there's lots of different type system out there, but so in the context that this is in, we're doing it in Haskell, right? And there's not really a formal definition of Haskell's type system, but it's like a Hindley-Milner style type system. Um, it's based on System Omega or System FC. It's called, if that means anything to you. But basically, so the thing that it's kind of it allows you to impart a very good specification to the compiler, but also uh, there's a lot of inference, right? So it's kind of picking the point in a type system where it allows the strongest guarantees in the types, but you can still infer everything, right? At least in the original type system. But then, of course, there's a bunch of extensions which have kind of changed it over the years, right? So, but type systems are good, right? They make sure that your code follows the specification. So you have some code, you give it a type, and then it basically checks. I infer the type of the code you wrote, and then I check it against the type that you gave me, right? And then you can kind of make sure that the code follows your specification, right? But type systems, they're not perfect, right? So the thing is that there's you give it a formal specification. That's what a type is, right? And as we know with formalities, right, there's no room. There's very little room for ambiguity, right? You can't really say, um, I want to leave some wiggle room here, or I want to leave some wiggle room here. Like you can parameterize over instances or interfaces or in Haskell we call them type classes. But but then it's still formally parameterized over an interface, right? So there's not a lot of room for ambiguity, right? And then when it comes to writing prototypes, you're kind of writing a program, but you're still figuring out like what do I want out of this program? What do I mean in the specification, right? So you kind of have a vague idea, and you often have a very shelled out idea, but we don't use the waterfall model of writing programs. Right? We don't sit down and write down the entire specification, and then we write down the specification in the program, and then we write the entire program. That's not really how, at least not how I write programs, right? So I like to have some wiggle room in my specification, but it's a bit hard to do that currently. So this is about how we can kind of allow for that wiggle room in some nice way, right? Okay, so I'm going to introduce like a running example, and it's called Mac. So the Mac library is a Haskell library. It's defined in this paper by Alejandro Russo, who's also at Chalmers. And so what does it allow you to do? Well, it allows you to define these kinds of labels. And what are these labels? Well, we call them low and high, but they're essentially you're essentially labeling a value with its security, right? So if it's high, then it's supposed to be a private value like passwords or credit cards or whatever. And then if it's low, then it's assumed to be public knowledge, right? So maybe your username or the web address. But it's kind of context dependent what is public and what is private. But what this allows you to do is that you kind of model in the type system the privacy of the data, and then you make sure that you don't actually accidentally leak private data by kind of inputting it into a computation which is kind of exposed to the public. So the idea is, let's make sure that we don't actually send out credit cards as a cookie for some reason, right? And in Haskell, we model this with this label. So this is kind of a data type, and then we use some type level magic. So a bunch of extensions are enabled, and that allows us to kind of use these labels in the type. So what we're doing here is that we're let me show you. So so this here is what we call like a phantom parameter, right? So we basically wrap whatever value we have, which is represented by this type A, could be a string, could be a number, and then we wrap it with a phantom type, which just carries the labeling information, right? So it's only at the type system. So here we have some values, right? So labeled one, like this is a string 1, 2, 3, 4, and this is like a value level thing or expression level thing, right? But we've labeled it as something private. So we're saying this here, a string is private information. So it's a string and it's labeled H, so it's private. And then we have 42, which is a public integer. So we label it with L, and we say it's an int. Oh, not an integer, but it's an int. Okay, so now we can kind of label values depending on whether they're public or private. But we need some way to kind of use that. So here's where security policies come in play. And we kind of define those in Haskell using these type parameter or type classes. So, but it's a bit of a trick, right? So we define a type class, but it's empty. It doesn't actually contain any runtime information, right? And we kind of define it to say, so it's basically like a type level function in some sense, right? So we say, less is less than or equal to, or low is less than or equal to low, low is less than or equal to high, and high is less than or equal to low or high, okay? So, and then we kind of encode it, so like we have an operation now on the type level, like a constraint that allows you to say that, this should not, so the only instance that's missing there is high is less than or equal to L. So when you try to compile something that needs the constraint, high is less than or equal to L, it will complain. So let's look at an example of that. So here we have a zip function, which is using this this class, right? So you take in a labeled list of A's, you take in a labeled list of B's, and then you return a list of pairs, right, of these lists. So it's just a zip function, but it's kind of in a labeled manner, right? We've kind of elevated it to the labeled level. And we model that by saying, okay, so we have X here and we have Y here, and then whatever the output is supposed to be, we say that, if so the input, the two inputs should be less than or equal to the output. So if you take in two public lists, then it's okay for the output to be public. But if you take in a high list, like a secret, like a private list, then we're not we don't allow that, right? So you send in a high level list and a low level list, and if you try to return a low level list or a public list, then what will happen is that either of these, like here, if we say that the if this one is high and this one is low and this one is low, then this constraint here will not be satisfied. So what's the example here? Well, here we have an example of a bad function, right? So the output here is low, and we're taking in two labeled lists. One of them is low, but one of them is high, right? It's a list of passwords, but we're trying to output it as a public list. So what happens here? Well, GC compiles, it does some constraint solving, and it will say, I couldn't find an instance for H is less than or equal to low. And that way you can kind of model the data privacy in the type system. Okay, So, but I talked about weakening, right? So, what is weakening? Well, so we defined it in this. We didn't define weakening per se, but we talk about it. Me and my co-author at Chalmers, Augustine, in this paper, which is it's at PLAS. It's going to be, which is in November, but it's been accepted, and we just have to kind of record a talk. Um, so, what do we mean by weakening? So the idea here is that, here we have an unsolved constraint, right? It's trying to solve the constraint that there needs to be an instance of this thing, but there isn't. So we allow it to be weaker. We will allow this program to pass. But instead of just saying we will solve the constraint, we will say we solve it and we also emit a message, which in this case will be a warning. So, and the thing is that with type systems is that you can't really talk about emitting warnings and stuff like that, because also you want it to be non-deterministic in some sense. You don't want to be like, okay, I can solve this constraint by emitting a warning, and I can solve it by not emitting a warning. Which one, and you can pick either one. You don't kind of want that. So we have like this metric also that only try to solve it with a message if you're unable to solve it without a message. And what you can do in GHC is that you can write plugins. So you can write a plugin to the compiler that gets called at specific points. And what happens? And these are one of these plugins is called type solver plugin, right? Or yeah, it's a type solver plugin, right? So what it does is that, whenever there are unsolved constraints that GHC couldn't figure out how to solve, it calls the plugin to try and solve it. And that's where we kind of inject these message generating rules, right? So we're saying, okay, we've tried everything that GHC knew about. Let's try these other rules. But so what we mean here is that we weaken the type system, right? We allow more programs to compile. But then it's the question, right? Are we allowing only well-typed programs to compile? And that's kind of we're kind of leaving it up to the user. We're kind of giving the user more freedom. So we might allow programs that are ill-typed to compile, but we're doing it in a one sense in a safe way, and I'll explain that later. But we're still generating more warnings, so we can still disambiguate between well-typed and kind of almost well-typed programs by the fact that there are no warnings. So what are the first thing that we allow is to ignore, right? Okay, here's a typing rule. We try to define the system a bit, which and I'm not going to walk too much through this rule, but it's basically saying if you're trying to prove some constraint and you have an ignore instance for that constraint, then you can solve it by emitting a message. So it's better explained in the paper, right? So what you do is that you have these type families. So this is a kind of a definition of a function, type level function in Haskell. So this is the type of the type level function, and here is the implementation. So what we're essentially saying is that we define an instance of ignore for this constraint here. H is less than or equal to L, which was the constraint that we couldn't solve earlier, right? But we also emit this message here. So you can define the message saying found forbidden flow from H to L. So this is called information flow control, the labeled Mac stuff. So what we're talking about flow here, because there's information flowing from high to low. And what does it say? Well, it turns the error into a warning. Okay, so let's look at the code here. Wait, hold a second. So here we have the kind of the instance of ignore. So here we have the labels. We're installing the plugin. There's a bunch of imports happening, right? And we define an instance of ignore. So we just call it less. We don't use less than equal to because it's I find it a bit clearer that there's not as many symbols going on. And what it essentially does is that we define an instance for it, and it prints out forbidden flow from A to B, and then there's some machinery here to kind of make sure that we're kind of printing out something nice now, some nice output, right? Okay, and then we test. Yeah, go ahead. Yes. Yeah. Yeah. So yeah. So what it does essentially is that so when it cannot find this regular class instance, it it asks the plugin, and the plugin essentially checks, is there a match for this rule here, right? You know, can I find ignore and then something that matches this pattern? Um, and you can see here that we're not just saying less HL, even though we could do that. We say less NM, so it's kind of so we're ignoring all constraints of this form. Um, and what happens then? Well, so here we have a function using this less constraint, right? And it's saying, okay, less LH, taking FH and FHB, so that doesn't matter. But the thing is that, there's nothing that happens here. This just works. Like GHC doesn't complain at this point. But here, we're trying to match something with less HA. And what that does is that because it matches this instance here, it complains. But that's because we have a general instance, right? So we kind of, so because it can't prove this, right? It doesn't really know the value here. Okay, so I think this is not the best example. The thing is that this HA here is being turned into a low, and I'll explain. It's a bit later. I'm sorry about that. But but what we're essentially looking at is this thing here, right? So it's saying I'm trying to prove less HL, and then we get the message here: forbidden flow from secret to public, which is the result of these two, right? But this is not an error. This here is a warning. That's why this line here is yellow. Um, and then, yeah, it would be nice if we could run this program without running anything else. Let's just do that. This is a live demo. Okay. There's a bit of a spoiler alert there. And then we will run this program, and you see it outputs these warnings, but these are not errors, right? And then it prints out the result, right? And then what happens is that if we disable the plugin and try to compile this, it just outputs a bunch of errors, right? It cannot find these instances for less. So it's doing its work, which is a bit nice. So let me just undo all of this. Okay, so so what this allows you to do is that it allows you to write programs with these less constraints. Kind of, you have them in your specification, but you haven't quite figured out how you're going to make it all match up in the end. And it allows you to ignore those constraints. So you can kind of prototype faster. And and a secondary kind of goal was also this, it generates a better message. This message here, no instance for less HL. I mean, I guess it's kind of understandable, but you kind of have to know what's going on here. And here we say, so, and this is an ambiguous type variable. So it's not really telling you so much, but but you get a clearer message, which is also something that we were aiming for. Okay, but that was the ignore rule. And let's look at what. So there we have a couple of other rules. So ignore is very general, right? It allows you to ignore any constraint. But in GHC, they don't. Not all constraints are equal. So there are some constraints which are like type equality constraints. So here we have the discharge rule. So like before, it's a bit of a complex rule, but essentially what we're saying is uh, we allow A to be equivalent to B if there's an instance of this discharge thing, right? So we have a similar family as before, but we have two parameters, and they have to have the same kind. So because A is a type here and B is a type here, and then K is kind of the type of types. So the types of A and B here must match, but the types themselves don't have to be the same. And then in this case, we can write this, right? We can say discharge L and H. So we can just say, whenever you're trying to equate L and H, you're allowed to do that. You can kind of discharge, you can throw that equality out and just kind of assume it to be true. And what? So let's look at the code there. So here we have the instance of discharge. Let's see. And it just essentially does the same, and it just says for any two labels, you're allowed to match you're allowed to kind of discharge those equalities. Like if you're ever comparing two types which are of kind label, like L and H, then you're always allowed to accept that constraint. And so, but another thing is like, why does this work? Like here we're ignoring a constraint, right? But the program still runs, right? So, why does it run if we're kind of not we're missing some stuff? And that's the title of the paper at Plaz. It's like weak runtime irrelevant typing. So the trick here is that because this constraint here is an empty constraint, it's just on the type level. It doesn't actually carry any methods or anything. At runtime, it doesn't actually matter. Like there's no information in that dictionary that is utilized at a runtime. So what we can do is that we can just throw it out. We can throw that information out, and it doesn't matter. And it's the same with the discharge, right? Because of these labels here, they only exist as like a phantom parameter. So the thing is that this thing here will always be runtime equivalent to it. Like the label here doesn't matter. Like the runtime representation of a private value and a public value will be the same because it's only type level information. What that means is that even if we throw out an equality of L and H, because we know that they are only going to be used as phantom type variables, we know that's okay. We know that we're allowed to do that in some sense. So let's see. So here we have the discharge rule, right? And so here we're trying to use that, right? So we have this max operator, which takes in two labels and returns the highest, right? So if either of these is high, then it will be high. If one of them is low, otherwise, if both are low, they will be low, right? And then it takes L1 and L2, and it's saying the max of these two should be high, but and we allow that, right? So and what it does is that you can see here that it doesn't even know what the types are. It just says max, min, max, any. But that's because we don't care. Like we have such a general label match here that we don't actually care what the value is. And I'll show you later how it works. But the idea here is, so we can kind of discharge equalities, right? So here we had like a class constraint to do it, but here you could say I want high to be low, or you could say I'm giving you like I'm statically encoding a private value, and I always want it to be private. But and then anything where it checks if it must be private, it will kind of use this kind of check here. But we always throw it out, right? And it's the same thing here. It will always it always works. Like it just gives these forbidden flow warnings. And let's see, we can not compile these, and then there's a spoiler alert. Okay, and then we can compile it, right? And then we get these warnings, but it still works, right? It can still print out the values, even if there's like a constraint being solved here that doesn't work. Okay, but so but discharge, like that's interesting, right? So we can throw out phantom type variables, which is kind of cool. But there is a special case, right? So what if the kind of discharge is star, right? What if we actually have base level types here? What if we're talking about int and string or int and integer? So there we have a special rule. It's not actually defined as a type rule, but it's defined as an instance of discharge. So here we say, okay, if you are trying to discharge, like you're trying to solve an equality of two types, which are of kind star, right? They're a base type. Then we have this new construction here, which we call only if, and it essentially says if you can coerce. So Haskell has this new thing, or new is like a couple of years old, which is called safe coercions, right? Which basically says that if two types have the same runtime representation, then you can safely coerce A to B, right? And it was kind of to replace unsafe coerce in some sense, because it doesn't really do anything else or different than unsafe coerce, except that it actually kind of emits a check. You have to check if they are coercible. And what things are coercible? Well, for instance, like kind of like these new type wrappers. So here we have a new type F, which is just a wrapper around this A here. So this is a constructor, and it has one member, it has one member. So it just wraps one value, and because GHC kind of optimizes all of that away, it will end up being like the representation of F in memory and the representation of A in memory will be the same. So, and that's, we say that then you can coerce A to be, you can coerce F to be A, and you can coerce A to be F, right? So we can do safe coercions here because they have the same runtime representation. So, okay, so let me see. Yeah, so, yeah, okay, wait, I was going to show you here. So this is what I'm talking about, right? So here, F, and F is just a wrapper around A, the new type. Okay, so we say that only if it's coercible. So this means that, we can discharge it if we know that it's coercible. And we'll see the only if definition later, but it kind of allows us to emit extra checks when we're discharging. And then you define these promote instances. So what do promote instances do? Well, they, let's see them here. They basically say, you're allowed to go from an A to a FHB if you can coerce A to be this value. And what does this allow us to do? Well, that's kind of cool. So we can discharge equalities between A and FHB if we can coerce A to be FHB. But then that means that we can use kind of naked level values. So this means that, so let's look here, right? So here we just have a naked true. Like we're not saying, MKF true, right? That would be how we construct a value of type F, right? But it's just the true. But what is happening is that, it's promoting an unlabeled Boolean to a secret Boolean, because we have a high here. So it's promoting this naked Boolean value to a secret Boolean. And then we have this operator called box, which that's what you should be doing. But here it's kind of nice, right? You don't actually have to say, here's a secret value, here's a public value, here's a anything like that. You can actually just use regular data types, uh, as you would before, but you don't have to wrap them. So, and this also works kind of within functions, right? So um, you can actually write functions. Let's see here. Okay, I don't have an example of that, but you can kind of write a function that just takes an unlabeled variable, um, and you can use that function with a labeled variable. It will just coerce the labeled value to an unlabeled value and then back at the end. So you can kind of use all the functions you already have, but you're kind of using them with this with these kind of values with added information, and it's okay because at a runtime they have the same representation. And you can even do it with things which are kind of also coercible. Like, so here we have an age, and that's just a wrapper for an int, and then we can treat an int as a public age immediately. We don't like we can it's like transitive through coercions, and it will warn here. So it's promoted from an int to an public to an labeled int, and then that is promoted, and that is treated as an age. I think this message actually might be improved a bit. Okay, and then so here we have something. So yeah, so you can use naked level values. Okay. So, but there's one more rule that's kind of interesting. Okay, so only if I talked about that a bit before. It's essentially saying, you can prove MA equals to MB. You can prove this only if you check the constraint and then you check the message. And we use it here. So it's saying basically, because how we do it is that we always just prove that this results in a message. So it says, you have to check that it's coercible, and then you can kind of continue by checking this promote thing here. Okay. And the last operation in this writ paper is called default. So that's kind of a bit of a complex rule, but it's got a very simple definition, right? It's just default k is of kind k. And what does that allow you to do? Well, it allows you to define default instances. So remember earlier here, we got, okay, this is a lot of output. Let me see. So we got an ambiguous type variable. And the thing is that, that's what's happening right here. All right, we're back on YouTube. Beep, 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 beep. All right, sorry about that. My OBS had a slight hiccup. I don't know. It's all untested technology, right? Okay. Where was I? Yeah, I was talking about default, right? So it allows you to. Oh yeah, now I have to fix this also. Let me see here. VS Code. Right. Okay, so it allows us to kind of default ambiguous type variables, right? So here it's saying, you're trying to promote something, but we don't know what the type is supposed to be. So we will default, the label here, L, the F in FL age to be L in this type equality that we're trying to solve. And then this type equality results in us trying to promote an init to a public int. And that's kind of nice, right? Because that allows you to, yeah, so here we also are promoting. But the cool thing about that is that, okay, so here we have a labeled maybe, right? It's labeled, but we don't actually know what the result is. So we default that to true, but it means that we can pattern match on, here is a value that's labeled, but we can pattern match it because we can coerce this just true here. By defaulting the label to be L, we can coerce it to be the value that we want. So default kind of wraps it all together. So now you can have types, you can have kind of things all over the place, which you haven't specified the type of. And you have and you can use those types as they were public or private. You don't have to specify that yet, and it will automatically go back and forth and marshal between them. And you don't even have to know what the public or privacy is, right? You can just default to either public or private. Okay, let me see. Okay, and that's kind of the what we have in the paper. But then, kind of work in progress right now is this dynamic stuff. So then we add two rules, and they're basically the same as the other ones, but they're specializations, right? So here you have, okay, you're looking at some expression E, right? And you're proving that the type of that expression A is equal to dynamic. But what we do then, so it's kind of an instance of this discharge, except it's specialized to dynamic, because instead of saying, okay, it's equivalent if you would say coerce, we actually say it's equivalent if you wrap it with a to-din function, which basically takes an expression and puts it into a dynamic in Haskell. So the backstory here is that Haskell has dynamic types, but you have to do this to-din and from-din wrapping all over the place, right? So, but we're doing kind of the same thing as discharge, the same thing as promote, except we're doing it, instead of always saying that the function that you wrap it with is coerce, we say if you're going to a dynamic type, then you use to-din. And if you're coming from a dynamic type, well, then we define this special function here, which we call cast-din. And it's essentially the same function that Python uses, right? It says, I tried to take a dynamic value and give you an A. And if there's a type mismatch, then I say, could match expected type with actual type, right? So because, at a runtime, if you have the wrong type, but you kind of, type system assumed that you had the right type, then you have to error out, right? And this is kind of cool, right? Because it allows you to use dynamic values at the top level in Haskell, right? So here we have the test in, right? And we have this extra thing here called Marshall Dynamics. And so here we have a list of x's, right? And it's a list of dynamics. But we don't have to-din all over the place, right? We just have a string, a unit, another string, right? A boolean, a number, right? And we have to say that it's an int because otherwise Haskell doesn't know how to convert. It doesn't have a num instance because, it can either be an int or an integer, and Haskell, yeah, so it's a bit of a backstory, but we have to specify that it's an int, but we don't have to say it's a dynamic, right? And then, oh yeah, okay, sorry. All right, takes a bit of practice, right? Okay, so here we have a list of x's, right, which is a list of dynamics, but it just has kind of top level naked strings, right? It's just a string. There's no to-din there, right? It's just a unit. It's just another string, right? It's kind of the same as you would write in Python, right? You just write whatever it is, and because Python always assumes that the type is dynamic, then it just works, right? But here we actually, in Haskell, we're adding this to-din function everywhere that it's required. And then we can run this code. And what happens here is that, okay, let me change it a bit so it actually tries to compile again. So, it emits a bunch of warnings, right? It's saying, you're trying to use a char as a dynamic, you're trying to use a unit as dynamic, you're trying to use a char as dynamic, you're trying to use a boolean as dynamic, right? But we're marshalling all that. We're doing to-din everywhere, right? And then so it actually compiles, and then it's also complaining here. So we print the list of x's, but because it's a list of dynamics, the default behavior in Haskell is just to print the type of it, like the type that's contained in the dynamic. But then, you have some faculties in facilities in Haskell to actually kind of do stuff with dynamics based on the type. So type level dispatch, essentially. So here we have a function that says, take a list of dynamics and grab everything that's a string, right? And we use that here. We say get everything in that list that's a string. And then, it prints out things I hated, right? And what happens here is that the next thing that we're trying to do is that we're trying to cast something that's an int to an integer, right? So, but the thing is that cast in here, if you remember from the slides, it takes in a dynamic, right? So this int here will be marshaled to a dynamic by wrapping it in a toDin, and then cast in tries to unwrap it again, but because it's trying to unwrap it at integer, it won't work, right? So we could also do it this way. We can say oops, take this int and treat it as dynamic, and then try to treat that as an integer. And then we try to run that, compiles, and then we get the same error, right? So it's trying to treat this dynamic here as an integer, but because we were marshalling an int, it doesn't work, right? But if we compile that out, comment that out, and we run it again, and then we see, yeah, so here we're trying to add two dynamics. One is an int and one is an integer. And the thing is that it tries, because this is an int, it knows that the plus here is supposed to be for ints. So it tries to kind of take this integer and take it back to an int, and that doesn't work. So maybe it would be clearer, actually, if we just wrote here, a, and that's not an integer, so that doesn't work. But, if we try to add a number to a character, it also complains, right? So could match to type int with actual dynamic type char. So then we kind of use dynamic types in Haskell, which is kind of cool. So the joke is that Haskell is the best imperative language because we have all those monad stuff, and now we have a kind of very nice syntax level operations for dynamics, which is cool. And people use Python a lot because they love prototyping in Python, and then they just never move beyond that prototype. They always just stay in Python. But now they can kind of get some of that dynamic stuff in Haskell. Okay, and that's all I have for you. So thanks for the talk. Thanks for having me, and I hope you liked the talk, even if there were a couple of technical hiccups. But yeah, so and the plugin is available. It's called the Red plugin. There's a link in the YouTube description. And I would post it on the chat here in Zoom, but the chat is disabled. So, but yeah, you can check out the description, and and if you want to read more about it, there's some details in the paper on how we do it, like what the plugin is trying to do and how it's solving things. And there's also a link to the repo itself, right? Like that actually has the plugin, so you can go test this out. And like one last thing I want to show you, just because we can, is we have this thing here, which is top secret, but it actually works, which is called test sin, and it's just a test. But there, we're kind of weakening things, and we're allowing typed holes to compile. So we have a program, and it has a bunch of holes in it, but we replace the holes with whatever matches the type. So we kind of synthesize the code here, and we just put it in the hole. So then you can kind of run this program, which has a bunch of kind of incomplete code in it, in the same way, right? We weaken it, and then we replace it with a function that you want, right? Which is kind of crazy stuff, and but we're not quite sure why you would want to do that. So that's we have to kind of find a good story to sell it with. But I think it's a fun kind of tidbit. Okay, yeah, thanks a lot. Yeah. Okay, great. Um, okay, yeah. So then I can post the link at least in the chat. Oh, okay, yeah, great. But but I left in the middle of the talk, so I don't have the chat uh from that point, right? So could you just ask the questions again? Yeah. Yeah. Mhm. Mm. Yeah. Yeah. So yeah, so what happens when it compiles the bad function with the plugin enabled is that yeah, it will essentially accept the constraint that you put there, so it will end up being having a low value, right? But the idea is that, but it's it's opt in, right? So you enable the plugin and then it ignores the security types, right? But once you publish your library or your package, then you would, disable the plugin and then you would actually have to deal with all the errors, right? So the idea is kind of while you're prototyping, fiddling around and trying to figure it out, you want to ignore all the security checks. And it's also important, when you're especially if you're a beginner. So I mean, that was kind of one of the main motivations, right? We were working as a group actually, and one of the members, didn't have much experience with Haskell, but also didn't have much experience with kind of security types, right? So we kind of we used them a bit as a case study in the sense that we're like, hey, try implementing this crypto algorithm using these static security types in Haskell. And they went ahead, right? And it was just like, this is very hard to make sense of some of the errors, right? Because it's kind of all embedded as a Haskell type error. And it's going to say like ambiguous type variable, could not match constraint. And you like, if you don't know Haskell, you can't read the error message. And if you don't know security types, you also can't even kind of try and make sense of whatever the error message is telling you. So the idea was like, but so we wanted for them to be able to um, write the code and check for functional correctness. Like you want to be able to know, does it actually work? And then you can check, does it implement security types, right? So this is also very useful for testing, right? So you can kind of write quick check properties or whatever and say, I want to test all this code, but during testing, I don't actually care about security types. I just want to make sure that it actually does what I want it to do functionally and not security wise, right? Because yeah, because otherwise quick check will just say, I can't do anything here because I don't know anything about security. So yeah. 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 So defer type errors, it essentially bakes the error into the runtime, right? So when you try to run code that has a type error in it, or like not the code, but like when you hit the expression, which is to blame for the type error in some sense, it will just crash with the type error message. But here it actually runs the code, right? It keeps going, and you can actually get the output, right? Which is, and if you're trying to make something work, but it has a bunch of complicated type that you're not quite sure, but but it turns out that those types don't really matter. Like all the runtime will be the same. It's just that you didn't fulfill some specific law that was encoded in the types. It can be very hard to understand what's going wrong. I mean, at least, I mean, that's how I work, right? I do a lot of like printf debugging, right? I just try and print the values and see what's going on. And then, that can be very hard if like, if there's a security error way up the pipeline and you just want to see, okay, but am I, what am I sending, right? So you will have a string and oh yeah, it turned out you were sending the username and not the password, right? And you can see that at the end of the pipeline, but because it wouldn't have accepted any of the security stuff, you wouldn't have known in the beginning, right? So it helps you kind of debug and prototype. But like I think the key is that it's opt in. Like you wouldn't want this by default. Like you don't want the compiler to just ignore all the types and just turn them into warnings, right? You still want some type errors, right? So that's how we allow it. Right? You define these instances, and that's the user writes these instances for his or hers domain specific language, right? And then that they can kind of impart their domain specific knowledge to what's okay to ignore in this case. Like, what am I trying to focus on? What do I not want to focus on? So, yeah, to answer the question, um, yeah, so deferred type errors will not allow you to run the code. It will stare at a route, but this allows you to still get some value of what you've written, even if it's type incorrect. But it's kind of it's it's a funny thing, right? So it's kind of a morally incorrect program that still works, right? So, and if you're used to Python, you can write so many programs that don't type check, but just because it happens that they have the same thing, it will work, right? So you have like an if branch that works, but the else branch doesn't work. And in Python, that just works, and that's very nice if you are prototyping, I think. And Python is a very kind of popular language, and I'm thinking, why not see if we can kind of get some of that goodness in, but as an opt-in thing, right? Yeah. Mm. 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 Yeah, yeah, that is true. Mm. Mm. Right. So I can actually, I can show you another example that we have, but it's a bit contrived. But we chose the security domain because it is kind of, uh, you know, it's not used a lot. These security types, these static security guarantees, because they're just too hard to work with. So our one of our goals was kind of how can we make security types better to work with. And kind of the thing was that you want to separate concerns, right? You want to focus on functional correctness and then secure correctness, and this allows you to kind of do that. But here we have a bit of a contrived example, I say. So we have vectors, but instead of being indexed by their exact length, we only know a bound on their length. We know how we know like the lower bound that they have at least some amount of numbers, or we don't know, right? And this can be useful in the sense that if you get some input from the internet, right, you don't know how long that will be, um, unless you kind of calculate it, but you don't really know that in the types. But you know that if you add 5 elements to the front of anything that's unknown, you still know that there's at least 5 elements. So we kind of wrote an example of kind of you have a length which encodes this there's at least n elements in the thing, and then if you have something you don't know the length of, then you just default to saying it's unknown. Um, and then uh, and then these vectors are just a wrapper around lists, except you kind of carry some information. And then you can kind of promote a vector. You can promote a list into a vector of unknown length. Like you can take any list and just make it into a vector. And you can go back, right? But this is like in the other example, like the two directions are a bit different here, right? You can only go from a list of A's to an unknown, right? You can't say I have a list of A's and I want to go to a vector length 1, right? Otherwise, you can't not an automatically via promotion. You can do that via an assertion, but not automatically, right? But you can always go back, and then it allows you to kind of define these safe head functions. If you have something that's has at least one element, then you can take the head of it, right? And then you can take a tail of something that has at least n elements, and then you will have at least n minus one elements. But if you take something from a vector that has at least one element, then you don't know anymore how much. So you always keep track of how much you know at least that they have, right? And then there's a bunch of kind of code around that. But the nice thing is here, so like this. So here we have a forget things, so we can forget that a list is uh, has some we can forget the length of the vector in some sense. But what is nice here is that I kind of wanted to show like this pattern match, right? You can have these kind of added information types, but you can still pattern match on them, but only if you have some sensible way of defaulting like the length here. We can default to unknown, and that's why we can kind of coerce a list into that, right? And then you can use these functions. Yeah, so like I said, I'm not sure. This is a good example, but like I said, it's kind of it's this thing that we're like any domain where you have some extra information, then you can kind of it's nice to be able to go back and forth by saying, I have the minimum amount of information about this value. And this is usually kind of, we usually talk about this in the sense of like a lattice, like in the security lattice. Oh shit. You have like a security lattice, right? And you have some kind of, here's the most amount of information, here's the least amount of information, right? And that's what we're doing, with security. We're saying if you don't know anything, you assume that it's public, right? And it's the same as like kind of with dynamic. I mean, that's kind of just an assumption, right? Yeah. Yeah. Mm. Mm. Yeah. 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 But the thing is, I think that there was some result at some point. I think that yeah, at least so. But I haven't seen the paper. But someone said that you can kind of almost always treat security values as being isomorphic to low or high, right? Because kind of in each specific instance, you're only really comparing, am I allowed to do it or not, right? You never have like a variable. You're never executing a computation and it says you're kind of allowed to do it, right? Only always in security you always have access or you don't have access, and maybe you have some partial access, but that just means okay, let's then you can always say, okay, which parts do I have access to and which parts do I not have access to. So it is in some sense always possible to make security into a binary thing, and that's why we use this example of binary information. But there is always this lattice, right? And there's always like you have the most amount of information, least amount of information, and if you can default into it, that should work. Yeah. Yeah. Yeah, yeah, and thanks again for having me. It was nice to be able to kind of show it and get some nice feedback, right? Yeah, yeah. Yeah, but I can stick around for a few minutes at least. Yeah, thanks. Mm. Yeah, yeah. You want to see the sneak peek, the behind the scenes? Wow, see, this is how it looks from the other side. I have a camera right there. But yeah, I have too much stuff, right? So it's been I haven't been able to meet anyone, right? But I always meet them. So, but I've been kind of doing a lot of virtual coffees, virtual dinners, and virtual meetings, virtual talks, and then I just decided might as well kind of use the money I would have spent traveling on kind of getting a nice setup. And it's very movable, right? So I mean, it's just I mean, because I am also into kind of recording music, so all the audio gear works for that, right? And the next part is just like having a good camera, and that also works because I can take a lot of nice pictures and videos. But the kind of the hard part is you have the two big lights, right? So they're not very movable, but they still they're still okay. I mean, and then but it's all very kind of it's a very nice movable setup, right? And then this here is it's actually a green screen, right? This is not my room. Uh, yeah, yeah, that's a trick. So, but the thing is that I took this picture with my with the same camera from the exact same angle. So if I take this off, you can see the green screen now, right? But then I it's like it was the same room all along, except I actually I cleaned it a bit, so the picture actually looks more worse than it actually is. But yeah, so it's a lot of space or Hollywood magic, but it's yeah, good stuff. Yeah, 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 yeah. I mean, it's yeah, I was in luck. I had my roommate moved out um a month or so ago. So I basically I took over the living room and just made it into a bit of a studio. And and I really so the thing was that I was attending ICFP, right? Which was virtual this year. And there was a talk by Alejandro Serrano. And he had this really nice slideshow, like video, like pre-recorded, right? Where he was inside the slideshow, big, but he was like taller than he was like, yeah, he had a better setup, right? So he had a kind of, it was his entire top body in the slideshow. And I was like, that is amazing. It looked so good. And it was so, um, yeah, yeah, it was so nice to see that, in a talk. Cause like, because we're still kind of learning, and there's not, because like if you're on YouTube, the standard is really, you have to be better than the other YouTubers, right? That's how you get watcher or like subscribers or whatever. The standard there is really high, but then, at conferences, the standard is, you're not accepted because of the talk you're going to give. You're accepted because of the paper you wrote, right? So I always can, so, I take extra enjoyment from when, people who don't have to kind of take the time and make like the extra effort to kind of sound good, kind of the talk looks good because they don't need to. There was some talks at ICP. I remember one in particular. I don't remember the name or anything, right? But it was like, and I would have mentioned it anyway. But it was just like a recording. Like it was not even like them with the slides talking. It was like a video recording of them standing next to a computer monitor with the slides and giving the talk, kind of. And that was, and it wasn't. It was a good talk. But the thing is, kind of because the audio quality wasn't so great, and then I think that's kind of what you really suffer from, right? In the sense that, if you go to a nice amphitheater somewhere, where conferences are held, you usually have good acoustics, right? That's why they hire those out as conference rooms. So you're kind of used to very good audio in talks, right? But even if you have good audio, you're still checking your email after 5 minutes, right? So, uh, you know, if it's not if it's not an amazing talk, then you're still checking your email. So that's also and online it's even worse, especially I think especially like at ICFP, right? Because like so what they did was that they had like these YouTube streams, right? They would premiere, there would be a session, and then there was a Q&A. Um, and because you could just rewind and watch the talk later, there was even less of an incentive to kind of be there, right? And I think this is what YouTubers have had to deal with for so long. Like, you start a video, and why should people like? So first of all, they have a clickbait title. Like, why did you start watching the video, right? I mean, for talks, that's easier, right? You either like the author, you like the abstract, you like the title of the talk, right? But then, even once you start listening to the talk, like if you're not one of the 4 or 5 people, you know, in the world that actually understands what the talk is about, you're probably going to zone out after 5 minutes, right? So you kind of have to have some incentive to like why should they why should I keep watching? Why should I keep listening to this? So and I think as as we evolve into more remote talks, I think it will evolve, right? I think or it will maybe not like the average will definitely go up, but I still think that because you can still deliver a fine talk just from your laptop, right? But that's why I really appreciate the people who go the extra mile to kind of bring kind of good content to your living room, right? Because there's not much else going on anyway, so you might as well spend your time doing that. Mm, 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 mm. Yeah, right. Yeah, yeah. Yeah, it's like 10:30. Yeah, right, right. Yeah. Yeah. Mm, mm, mm. Yeah. Yeah. Yeah, yeah. Yeah. Yeah, yeah, yeah. Right. Yeah. Yeah. Mm, mm. Yeah. Mm, mm, mm. Yeah. Yeah, yeah. So that's kind of what we were what I was thinking about with this respect to the synthesis stuff, right? So because because then you're kind of so you have all these typed holes, right? And some of them might have you could imagine a function that takes a function and then takes a list, and then returns just a map, right? But depending on how you synthesize that map, you might synthesize a parallel map, right? And you might synthesize a parallel map that splits into n blocks, or just runs through the first two things, and then so, and that's kind of the one of the ideas that we're like I'm interested in, is like kind of can we strategically place holes in our algorithm where we say we can parameterize over this expression, right? And then you write a synthesizer that specializes the program, right? So it's a bit like so yeah, I don't want to say partial compilation, or like because that's a very specific thing. But it's a bit like because because you have the program, and then you can parameterize over if it should be sequential or parallel, or in which way it should be parallel. But what you usually have to do now is that you have to kind of write, here is a function which implements this interface. It's like a runner, right? And then you input a runner into it, right? But then the thing is that when you select that runner, that is not that is determined like during like you kind of have to pick it before you compile the program. But the cool part about this is that you actually are compiling the problem. You're compiling this module of the program, so you have access to the source, right? So then you can see. Um, so one example I like to take is if you have you're selecting between between queues, right? If you want to have insert heavy queue or read heavy queue, right? And then you can read. If you look at the source, you can kind of figure out which one you should pick, and then you can synthesize a function that matches that one, right? And you don't have to know what the function is. Like it's kind of like just-in-time compilation, except instead of happening in at runtime, it's just in time during compilation in some sense. So so it's not really just in time compilation. It's kind of just in time instantiation or something like that, right? And I think especially if you're doing GPUs, you're often kind of picking, there's a bunch of kind of hyperparameters, right? How am I going to split this into different work loads, right? And it's very nice if you can pick that not at runtime, because then it's kind of too late. But if you can pick it when you are like, so because this kind of pushes the choice to the last possible instant, right? You are actually looking at the parameter, and you have to pick one right now, or else it will be too late. And then you can have all the information that you can possibly have to make an informed choice at that point, right? um so yeah, yeah, right, yeah, right, right, yeah, 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 mm, yeah, yeah. And because that's the thing, right? Because if you do it at runtime, you don't get any compile time optimization, right? You can't kind of, because you want the optimizations, but you also want the specialization, right? And this kind of allows you to make that trade-off at the latest possible stage in some sense. And then because it's like it's doing synthesis, right? So it's coming up with the expression that you want, right? So but so another connected idea is the idea of kind of overlays, right? Which is just, it's basically a synthesizer, except you already have a file of kind of saved syntheses. save things that you synthesized before, right? So then you can say, you know, run this module with these parameters, run this module with these parameters, right? And then you can even say, run this module with these parameters, but you're allowed to pick new ones for this one, right? So, and then you can kind of save the overlay, and then you can kind of bake it in, right? So, but yeah, but it's still it's a bit of a hard sell, right? Because like yeah, GPU applications is cool, but then but the thing is that the synthesis itself is kind of orthogonal to the actual thing we're doing, and if you have bad synthesis, then it's not very interesting, right? If you just pick anything, then you're not really getting any cool results. So that's kind of our issue here is that we need a good kind of story there. But if we figure that out, then I think it's good stuff. And then we're in the process of trying to kind of write a more general paper about this. But yeah, so we'll see. We'll see how that works out. Hmm. Yeah, yeah, and yeah, and thanks for having me again. You know, I always like giving talks, so it's always fun to get a chance to get an audience and get especially like on current research because once you have to tell people about it, you kind of because I moved the synthesis stuff from the talk itself because it's more out in the air. But I was initially going to have it in the talk, but then I kind of figured out, okay, this isn't really where it's at to where I can begin talking about it. And it's nice to always get that kind of fact check. Can you if you can give a talk about it, then you actually know something about it. But if you don't trust yourself to explain it to someone else, you shouldn't be making any claims either, right? So I think it's a yeah, exactly. Yeah. Okay, but yeah, 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 yeah. Thanks again. Yeah. All right. So now I say goodbye to the Zoom people, and for you watching on YouTube, thanks for coming. I hope you liked this talk. Uh, Sorry about the late start. We had some technical issues, and then OBS froze on me, which was a bit sad. I did put the encoding at super high, so maybe that was the issue. And I really hope because I did try to record this thing, but at least YouTube has the recording, yeah, so it works. Okay, yeah, and thanks again for coming, and yeah, so leave a comment if you have any questions, and yeah, catch you later.